Hi everyone, it's Sam Alcaine from Cornell University. I'm going to be giving an update on a project that's essentially complete called Fermenting Value for Dairy, where we're looking at skim milk utilization. I do want to say one thing. I don't know if you can notice by looking at the screen, but my title has changed from assistant to associate professor. And I just want to say thank you to the Dairy Promotion Board. Without your support over the past 6 years on research projects and looking at forward fermentations, I wouldn't have been able to do this. So thank you very much. And now we'll go back to chatting about the project. As kind of a quick refresher, the idea here was that skim milk demand has been going down, and so sometimes we're left with excess skim milk or excess skim milk powder. The question is, what could we do with it? So our previous work had been looking at Brettanomyces, which is a type of yeast that can utilize lactose, and we found that under certain conditions, if you split the lactose into glucose and galactose, the yeast would utilize the glucose but would leave behind the galactose. Now, this was in dairy byproduct waste streams, but galactose is a very interesting sugar because it's low glycemic. It's good for the brain. It's converted to hepatic glycogen in the liver, right, which is kind of the powerhouse for your body when you're doing exercise. So it might be valuable to have excess galactose. So you could use that as a sweetener in beverages. We could also produce alcohol. And then maybe that excess galactose could also then be used to optimize other processes like galactoligosaccharide production or going to food ingredients. So this is kind of the whole ecosystem that we're trying to play in. So the question was, what would Brett actually do in skim milk, right, as opposed to permeates and waste streams? So the goal of this project was to evaluate the fermentation of skim milk and milk concentrates by Brettanomyces and benchmark it against related yeast species, and then optimize some of those parameters to see if we could improve galactose production from skim milk. So the first set, we basically looked at fermenting skim milk by Brettanomyces and 3 other yeasts, Brett bruxellensis, Cluvaromyces marxianus, and Saccharomyces cerevisiae. And the takeaway here is when we were fermenting out the skim milk, you can see it didn't look that great. And we didn't have a lot of residual galactose. We had a little bit here from the Bretts that we were looking for, but not as high as we were seeing in the dairy byproduct waste streams like we saw with yogurt whey or whey permeate. So the question was, what could we do to improve this? So we went back a little bit to the drawing board, and we were inspired by a product called Calpis out of Japan, which is another fermented beverage that does have skim milk powder in it, but at lower levels. So we reduced the skim milk protein content. That also reduces the amount of sugars that were present, so it might increase the fermentation time. And then what we did is that we acidified it, and this is the process they use for Calpis. They acidify the protein, they heat it, and that makes the proteins more stable so they won't coagulate. And then you can see here, so there's the acidification and then the heat. And so we did that, and we took that base and we fermented it, and it looked wonderful, right? You can see the product there. And the other big thing was, now while we did start off with a lower lactose levels than we would in regular skim milk, right, about half, what we did see here is that we had a high retention then of the galactose by the Bretts, so over 60%, which, hey, there we go. Now we have a galactose-rich stream that could then make an interesting beverage. And actually, the initial organoleptic tastings of this were very, very positive. So that was a great sign. The next piece that we wanted to do is to see also, could we optimize these fermentations by changing the amount of lactose, and subsequently when we hydrolyzed the lactose, the amount of galactose that was left over. And then also, could we then optimize the amount of yeast that we use? So what we did is we looked at 2 different solids contents here, and then we looked at 3 different levels of the Brett Clausenii, and then we fermented it out and we looked for final galactose levels. And what you'll see here is, while some of them were low, this interesting combination, which was very consistent at 5 times 10 to the 7 CFU per mil, if that's what we added the yeast at to the concentrated milk, and we had 100 grams per liter concentration of the lactose to start with, we would be left with around 25 grams per liter of the galactose, which is great, right? And everything else was fermented out, right? There's really no glucose left and essentially no lactose. So that was a really high percentage of remaining galactose, which means then we could then take skim milk powders, selectively ferment out the glucose, and leave a galactose-rich stream, which could then be used as an ingredient for other processes like galacto-oligosaccharide production, extruded products, things like that. And so, in the end, right, we were able to successfully show that Brettanomyces claussenii under acidified conditions would retain 65% of the available galactose and allow us to make galactose-rich beverages that still had dairy protein. And so now we can do work on then optimizing what those flavors should look like. And you can see something like a strawberry milk or a chocolate or something like that. And then we also showed that if we had high solids content in non-acidified milk with this pitch rate, we were able to retain over 68%, so nearly 70% of the available galactose, and then that could be used as an ingredient source for foods, beverages, or other processes. So we did note, right, that acidified product that was kind of like Calpis had the best taste and sensory profiles from what we tried in the lab, and we think then there is a great potential to create galactose-rich beverages and other ingredient streams. Now, that's kind of, the whole arc of what that project was. Some of the other outputs of this were that, again, back in 2021, the graduate student who was working on this, Lucas Wise, won second place for the presentation of his work at ADSA. And then this year, Lucas over here on this end of the screen graduated with his master's, so we're super happy for him. He's going into the fermentation industry, so that's exciting, right? He's caught the bug. He's written his thesis, and now we are just modifying the manuscript to get it submitted so that we will have a peer-reviewed publication of this work out there for other people to read and follow. So it's a great project, super interesting, super successful, and it was great to do. So again, thank you for your support, and I will be happy to answer any questions when we have the virtual live meeting. So take care.